So in this video, we're going to recap free body diagrams, equilibrium equations, and supports. So the first topic is free body diagrams, which is abbreviated to FBD. These are diagrams which show all the forces and moments acting on a body. Okay, so an example might be, say you have this wall here, and you've got this little bar that's sitting against the wall, and you wanted to draw the free body diagram of it. You'd separate out just the component of interest, which is probably just the bar, and draw all the forces that act on it. Now, there's a little bit of a trick. When you have these, like, I'm going to call them smooth surfaces, let's assume that they're smooth. That means that there's no friction acting. So the only forces are going to be normal forces to the surfaces that your body is resting on. So if it's resting on a vertical wall here, the reaction force, or the normal force, is going to be horizontal. And I'm going to call it N1. Similarly, if this is a horizontal ground, the reaction force is going to be perpendicular to that, so it's going to be vertical and straight back up. Okay, so that would be an example of a free body diagram of a bar leaning against the wall, and the only other thing that you might want to include on it is the weight of the bar itself. So you'd probably put that through the center of gravity, assuming that it was a uniform bar that should be at the center of the bar. The only other trick with these normal type forces is sometimes you might have the situation where you have a bar leaning on a corner. Let's make that a little bit more vertical. So let's say you have your bar looking like this, and maybe you have some other forces acting on it externally. Let's call it P1 and P2. Alright, if you were to draw the free body diagram of this situation, again you need to take out your bar. You can transfer over your external forces, and again you're going to have a reaction caused by the fact it's contacting a surface, but this time, because it's contacting a corner, the force, or the normal force, is going to be applied perpendicular to the bar itself, not perpendicular to the contacting surface, since it's a right angle. So it should be 90 degrees to the bar. So I'll call it N. That here needs to be a right angle. Okay, so that's pretty much the only tricks for free body diagrams of very simple shapes, like things like bars. So now we'll talk about the more complex cases, I guess, which is where you have supports. So there's three different types of supports that we can have. So the first one that we can have is called a roller support. These ones typically have a symbol that looks like this. So they're on little wheels that are able to roll along the ground. And you're going to have a little pin connection up here at the top. Let's pretend there's a member connected to it off the end, and that pin is going to allow free rotation of the member. So the only way that these roller joints react is perpendicular to the surface that they're sitting on. So if this is a horizontal surface, it's going to react perpendicular to it, so vertically. Potentially it could also be downward as well, but this is just generic. So the next type that we have is a pin joint, and it's similar in look. Again, it's got this little pin here, so if there's a little member coming out of it, it's going to be able to rotate freely. But this time it's not on wheels, so it's stuck in the ground, which means it's not going to be able to move up or left and right. So it's going to be reacting in two directions, horizontal and vertical. So you can replace your pin joint with these two support reactions. The other type of joint that we can have is a fixed one. Okay, so this might look something like so. Alright, this is the member here. So it's stuck in the ground. You can think of it as being like cemented there, which means it's not going to be able to move up and down, it's not going to be able to move left and right, and it's not going to be able to rotate. So instead it's going to provide support reactions in all those directions. Okay, so horizontal, vertical, and a moment for the fixed joints. So the only other kind of thing to discuss here is the equilibrium equations, which can be used to solve for unknowns on your free body diagrams. So there's three that you can use. So the first one is that the sum of the forces in the x direction have to be equal to, 0. The second one is sum of forces in the y direction have to be equal to 0. And the third one is that the sum of the moments about any point on your body have to be equal to 0 as well. So the reason they're called equilibrium equations is because we get no movement. And if you think back to Newton's second law, which I almost wrote down a second ago, force is equal to mass times acceleration. So if you're looking at a dynamic scenario, if you were to sum the forces in the x direction, you would expect that it would be equal to the mass times acceleration in the x direction. But since we're looking for no movement, okay, no acceleration, we say that sum of forces in the x direction is equal to 0. Same thing with this. If you were to sum in the y direction, if you had a dynamic situation, acceleration would occur in that y direction, but since it's static, there is no movement in our structures, this becomes 0, so we end up with our equilibrium equation, sum of forces is equal to 0. Same thing here happens with the moment equation. It's a little bit more complicated in terms of the look. So sum of the moments is equal to, it depends on your situation, but it can be equal to some equation that looks like this. Because it's the moment and you've got rotation, alpha is the rotation thing, so you want no movement, so no rotation. A again is your acceleration. Linearly, you want none of that, so it needs to be equal to 0 as well. So basically everything needs to be 0 for us to have no movement and our structure is stable, not moving. So that's all there is for the equations in this topic. All you really need to remember is these equations here, how to simplify down each of your different support reactions, and finally, if you have a situation where you have something leaning against a horizontal, vertical, or whatever else surface, you need to apply the normal force perpendicular to the surface, or if it's leaning on a corner, like this other case that I drew in the middle here, then you need to have your normal force applied perpendicular to your member. So that's all there is. There's several examples. See you in those.